So obviously answer to today's quiz is not that resistor is a device which resists current. It is a device which performs a precise function, and the answer requires actually that you specify what function it performs and make and describe it unambiguously. So a resistor is a device which has two sides, and potential difference across the resistor is always proportional to the current flowing through this resistor. And consistently with this drawing, if we mark current, let's say to the right, then potential difference which relates this current with is we will have to subtract from potential, which corresponds to the tail of the arrow, potential which corresponds to the head of the arrow. If you do it this way, you will be always able to solve a problem which involves, resistors in a circuit. All right, now let's see what happens if we make arrangements, if we connect resistors. Let's start with what happens if resistors are connected in parallel. Actually, this connection is not that important as the other one, because the only time, well, no, actually, there is an arrangement in which you probably use parallel connection. So I will not condescend this type of connection. Well, let's recall that elements are connected in parallel, that potentials on corresponding sides are equal. Not voltages, not potential differences, potentials themselves. So potential on the left-hand side of the top resistor is equal to potential on the left-hand side of the bottom resistor. And potential on the right-hand side of the top resistor is equal to the potential on the right-hand side of the bottom resistor. If I now this system also behaves like a resistor, which means that, what does it mean that a system behaves like a resistor? That the potential difference across the system is proportional to the current flowing through the system. So I will have to consider current entering the system. This is current flowing in this wire over here or in this wire over there. Should be proportional to potential difference between this point and this point. Now look that already that if we have two resistors, we already have three currents. Do you see that? Three values of currents. I'm talking about the physical quantity. Now actually you can think about a physical quantity, because there is a kind of a slang word which would make actually sense to introduce at some point. So this way, well, at least in that slang, people distinguish between the phenomenon and the quantity, because phenomenon, flow of charge, is called really current, and then the physical quantity is called amperage. However, I prefer that you don't use it, because a proper phrase now is still current. And amperage it has to be expressed necessarily in amperes, although we usually do it anyway. So where do we have those three values of the current? Because we have current flowing over here, and now some of charged particles flow up, some of them flow down. So we have different current here and different current here. We have three currents: one current here, one current here, and one current there. There are three currents. Well, but we have to know which current has to be related now to which potential difference, although potential differences are going to be the same indeed for all three, in order to verify that the system behaves like a resistor. So we have to relate current flowing into the system. So this current, I can recognize that this current, some of particles flows up and some of particles flow down, which means that current entering the system must be equal to the sum of currents which flows through the two resistors. And if we have more resistors, I can write down that there is all of them, as long as they are connected in parallel. Now, for each of those resistors, I know that Ohm's law is satisfied. And Ohm's law says that potential difference across the resistor is proportional to the current. Well, so I can reverse it and say current is proportional to potential difference. And I will have to divide potential difference by resistance of the resistor in order to get current in the resistor. So this current will be potential difference across the top resistor divided by resistance of the top resistor. Current in the second resistor will be potential difference across the resistor divided by resistance of the resistor, and so on. However, if they are connected in parallel because corresponding potentials are equal, then voltages or potential differences are equal as well. So here, everywhere I have the same number, I can factor out this number. And if I factor out this number, it should make me happy. Do you see that? Adam, do you see it? Because, well, Adam said that we have to show that current through the system is proportional to the voltage across the system. And we got it. Now, this is proportionality coefficient. However, this is not resistance. Resistance should be on the side of the current, which means that I have to move this entire expression to the left-hand side, and I will have that potential difference is equal to current times resistance, which means that the inverse of equivalent resistance of resistors connected in parallel is equal to the sum of the inverses of the resistances of individual resistors. Let's now take a look at what will happen if we connect resistors in series. Well, if we connect resistors in series, then we can recognize that current, well, first of all, if they are connected in series, it means that at any time the same amount of charge enters each element. So if charge dq enters this element, charge dq enters the second element. If I divide it by the time in which it enters the resistor, I will get it in terms of currents. If elements are connected in series, currents flowing through the elements are equal as well. All right, let's now check if this system behaves also like a resistor. And indeed, I will show that it does. Again, Adam, what do I have to show? That the potential difference is proportional to the current flowing through the system. All right, so I'm taking potential difference across the system. Now, if I think about potential difference across the system, it's potential difference, since I marked current to the right, I have to subtract from potential on the left-hand side, potential on the right-hand side. This is going to be potential difference across the system. Now I can make a mathematical trick over here by adding and subtracting potential at a point in a point in between the two resistors. I mean, these two add up to 0. So indeed, this is true. Now I violated actually the equation, and if I had more resistors, I would write more of those terms. So this would be a potential difference at point A minus potential difference between point A and the last point which I have over here would be Y. So it would be V sub Y. All right. Now what this potential difference is across the first resistor, which means that it is related to the current in the first resistor. But it happens that it's the same current as current flowing through the entire system. So I can write down that this is current through the first resistor multiplied by resistance of the first resistor. The second one is current flowing through the second resistor times resistance of the second resistor, and so on. And I see that somebody has a question or something is ambiguous. Eric, what's the problem?
I think that one of the ends should be Vy minus Vz to say.
Oh, I mean because of alphabet, right?
Yeah.
Oh, it doesn't matter.
Okay.
Yeah, it's true. That's fine. I mean, I could put whatever I want. I mean, 1, 2, 3, 4, and so on. But I'll change it. Okay, I'll do that. Now I see that I have common factor here. Current through each resistor, which happens to be the current through the system, so I can factor it out, and we should be happy because we have already shown that potential difference across the system is proportional to the current flowing through the system. This is the proportionality coefficient for the system, which means that this sum represents equivalent resistance of the system. So equivalent resistance of the system connected in series is equal to the sum of resistances. This connection is actually quite important in a circuit, and I wanted to bring up some applications of resistors. The most common application of resistors in a circuit is to establish potentials in the circuit for other devices, something like integrated circuits, like transistors, thyristors, and so on. Those devices need to be properly polarized. They need. We have to connect them to appropriate potentials. They will not operate if the potentials are not right. And in order to achieve those potentials, we have to find an electronic system or arrangement of elements which will do it. Now, let's think what kind of batteries we have, for example. So let's say that we have something which requires a 9-volt battery. I don't think iPods probably don't. What is the most common device which you have over here? Who have cellular phones? Yeah, cellular phones. Now let's see. I don't know actually because the battery is not a common battery, and then each manufacturer makes its own battery. So I don't know what potential difference the battery itself produces. Okay, but let's say that we use a battery which produces 9 volts, and we want to use it in a portable radio. And there are various transistors over there, and a base of a transistor requires half a volt. So potential, we have to make sure that potential at the base is half a volt compared with the lowest potential in the circuit rather than 9 volts. Well, how do we do it? With resistors. We use an arrangement which is referred as a voltage divider. So I can connect here 9 volts, and I say that I will choose the lowest potential in the circuit as the reference. So in principle, if I have this 9-volt battery, that minus on the battery, I will assign 0 to that minus on the battery. So potential of the minus terminal of the battery is 0 because I can do it, and then consistently the other terminal will have potential of 9 volts. Correct. Now how to get half a volt from that? Using voltage divider. So I connect 9 volts over here. So this is plus of the battery, this is minus of the battery, and here I can have half a volt. Let's see why does it work. So potential at this point, I can find out the potential difference between this output potential and the negative terminal of the battery is related to the current. It is potential difference across this resistor. Can you see that? All right. So if it is potential difference across this resistor, it means that it is proportional to the current flowing in this resistor. I can write it down that this is current flowing in this resistor multiplied by resistance of this resistor. Now the current flowing in this resistor is related to the current flowing in that circuit. Now assuming that whatever I connect over here doesn't drain a lot of current, these two resistors are connected in series. So I can find that their equivalent resistance is equal to the sum of the resistances. Now I have 9 volts across the system, so I can find the current flowing through the system and therefore through that resistor. Current is going to be equal to potential difference across the system multiplied by resistance, equivalent resistance of the system. And if I rearrange it neatly, I will get that output, that potential over here is equal to potential over there multiplied by this fraction. Yes, so let's say if I wanted half a volt from 9 volts, which means that this quotient should be 1/18. So I can adjust the values of resistances in such a way that this quotient is equal to 1/18. Now it's not unique actually. I can have, let's say that R1 is equal 1 kilo ohm. If R1 is 1 kilo ohm, then R2 should be 17 kilo ohms, and this would make the trick. Potentiometer is actually even, it can, on the same basis now, I can use a resistor as a current limiting device in the circuit. Yes, so for example, if I have battery which operates at 2 volts and I want to have it in a circuit and connect it to 9 volts, I can connect it through a resistor. This system also really works like a voltage divider. Let's say that resistance of the light bulb is 1 ohm. What kind of resistors would I have to use in order to have, let's make 3 volts. You have this one, if resistance of the light bulb is 1 ohm and it operates at 3 volts and I have 9 volt battery, what resistor I should get over here? Well, I should get 1/3 of the voltage provided by the battery, which means that resistance of this resistor should be 2 volts. So if I put 2 ohms. If I put 2 ohms, connect to 9 volts, it's going to work because we will connect the right potential difference across the light bulb. The operating potential difference for the light bulb is 3 volts. So I take a 3 volt battery, 3 volt light bulb, and I want to connect it to 9 volt battery. I will have to use a resistor, and now look, that resistor together with the light bulb forms a voltage divider, and it is quite common way of dividing voltage. We don't necessarily have to use it like on the previous slide. So for example, we can use a base of a transistor also, consider its resistance and bias properly transistor. Robert has a comment or a question. What's the question? What is it?
Is the light bulb R1?
The question is what is the resistance of the light bulb? And indeed, resistance of the light bulb over here is R1. It's consistent with the previous drawing. And Andrew has something.
It doesn't make sense to me. Predictably, that wasn't clear on the last one. How where the out does that disconnect back and basically almost where it starts, or it seems like it's a open potential. There's no way for current to flow.
On the previous one.
Yeah.
Not right. It is. This arrangement is for a case that whatever is connected here, like input of a transistor, like field effect transistor, for example. This transistor consumes very little current, practically zero. Andrew is right that in order actually to make this step, I assume that current flowing over here has a zero value, because only then we have that current flowing in that bottom resistor is related to that input. Now, if we have something, because actually, if I have something which takes a substantial current, then I can consider this entire a combination of the resistor and whatever is connected as two resistors connected in parallel, and then this would be R1. Is it clear, Andrew? Yeah, and for everybody? Right, I mean this is actually what happens with the light bulb. Now that R1 on the previous picture is thrown away, I just use whatever is connected as a part of that voltage divider. Now, sometimes we even use this voltage divider to adjust potential at a particular point. So if we want to control volume, for example, this way we can affect what fraction of the signal is taken. So here we have input is the signal coming, let's say, from certain amplifier, and by, well, potentiometer is it's not already a resistor because it has three terminals, and but it works like a voltage divider. Now by sliding the connection over here, I can change the ratio of the two resistances and adjust the output voltage to whatever value I want. If I slide that contact to the left, to the bottom, the output will be 0. If I move it up, the output will be equal to the input. All right. And here is a picture of a potentiometer, a real potentiometer, which we use in a radio or TV. Well, we are stopping doing it anymore, right? Because I mean, that one would be connected to a knob, and then you would have to turn the knob. And nowadays, you just push a button. All right. Now what did I do? Okay. Well, here's another application of a resistor. It is that we can use it as shunts. And a shunt is a device which creates an alternative path for current. So let's say that we have well, something. It's a circuit, although I represented this as a resistor. So think about that right now, that it's just a resistor. However, I anticipate here currents which cannot flow through this resistor or through this part of the circuit. It would damage whatever we have over there. Like, for example, I don't know if you already had an experiments with making an ammeter and a voltmeter. In an ammeter we use, for example, a device which is called a galvanometer. And galvanometer can take only a few milliamperes flowing through it. And I want now to use it to make a device that technician can measure with this currents of an order of 10 amperes. Well, how I can do that? Well, I have to use a shunt and create an alternative path for the current. So not all the current which is measured flows through the galvanometer. What I do is I have to connect a so-called shunt resistor, and it creates an extra path over here. I'm not going to derive that expression, but now current flowing through the part of the circuit in which we want to limit or reduce current is a fraction determined by the shunt resistor. Look that, note that if shunt resistance is infinite, then all the current flows through that circuit. But if I take shunt resistance relatively small, or let's say 0, which doesn't make sense actually to do that, but if I take it as a 0, then no current would flow over here. So shunt actually is something like a current divider. It divides current into two alternative paths. And here is a picture of a shunt. And note that a shunt resistor, I mean, just looking at the picture, anybody can recognize what material is used to make shunt from the color? Brass, yeah. It looks to me like it's made from brass. Brass is a very good conductor. Now take a look at the length and the cross section of that shunt. Does it have high resistance or small resistance? Who votes that it's high? Who thinks that it's small? Well, there was more support for high. However, the correct answer is small. Look at the cross-sectional area. Recall that resistance, when we make a resistor, how about if I write it down here? Resistance of a resistor depends on the material, on resistivity of the material. It's proportional to resistivity of material. It is proportional to the length of that resistor and inversely proportional to the area. Now that one is short and thick. Cross-sectional area is relatively large and it is short. So, and on top of it, we take a good conductor, which means that resistivity is small as well. And therefore, resistance of this shunt is probably a small fraction of an ohm. Robert has a comment or question.
The cross-sectional area of that wire is being compared to, or of the resistor is being compared to the wire?
No, actually it is compared to the cross-sectional area of a wire which is used in resistors.
Okay.
And
I guess I just don't know what.
Well, yes, yes. So you can compare. I mean, this is almost the diameter of a wire. You saw a wire, right? And actually, it's even probably thicker than a wire. You see that this is as thick as the wire over here. Now, you remember that every wire is a resistor, right? And every wire is supposed to be a resistor with what resistance? 0. It is supposed to be. It never is. So so we are losing some power in resistor in wires because of that. Oh. Oh, here I have a, and actually, note. I mean, look at these two. Do you see the? Do you see that these two? I mean, what is the purpose of it? To connect it to whatever you want to, in whatever you want to reduce the current. Yeah, so this would be connected to the galvanometer, for example, in your experiment. Is it the next one, or when are you do you know when are you going to build an ammeter and voltmeter? You did? Oh, using galvanometer is not the same thing. No, because you were using it in a Wheatstone bridge, right? So you were balancing the bridge. Over there, actually, you were using a resistor to protect the galvanometer. You had that limiting function of a current limiting function of the resistor. One of the previous slides in which we use a voltage divider. It works like a voltage divider. No, but you will now use a galvanometer to build a meter, both voltmeter and ammeter. All right. Now, whenever current flows through an element, well, maybe not whenever, but electricity can deliver energy to a device. And how much energy is delivered to a device depends on this: what voltage and what potential difference and what current flows through that device. In general, electrical power is the rate at which electric field performs work on the charged particles. Now let's try to establish, it's not necessarily a resistor, let's say that we have a certain element, and there is a certain current and a certain potential flowing through this element when certain potential difference exists across this element. Let's say that potential at the top is V1, potential at the bottom is V2, and see what will happen if charge dq moves from one side to the other side of this element. So actually, charge dq enters on this side and equal amount of charge exits on the other side. What will happen by how much energy will be delivered to the system, or how much energy will be delivered really to the charge carriers? All right. So power is the rate at which work is being done. Right? So I have to write down that it is the rate at which work is done. So if I consider time dt, I will calculate how much work is performed in time dt, and in time dt, this time dt corresponds to the charge dq entering from this side and exiting from that side. So practically we can think that charge dq was transferred from one side of the element to the other side of the element. Well, so it's easy to find out what is the work, what is the electrical work, because it is opposite to the change in potential energy of this charge dq, of the charge of those particles. So it is charge of those particles multiplied by potential difference. Now note that here I have this product gives me potential energy of particles over there. Now this product gives me their energy when they were on this side. Now it isn't true that these are the same particles, because there are, let's say, an electron enters here and electron exits there. It is that for our purposes we can think that an electron was transferred, although this is not the same electron. Yeah, but the amount of electrons which are here is still the same. Do you understand me? It's not exactly the same, but it is like just one electron were transferred. All right, now this dq is a charge which enters on this side and exits on that side. So if I divide it by time in which it exits, what am I going to get? Current. The answer is current. Now which current? Because remember, current is always through a surface. So which surface? Yeah, I said that charge dq entered at terminal 1, at stop 1. Now, it happens that it's the same as at the other end, at the other surface, and any cross-section, which means that this quotient over here gives me current flowing in that resistor. So I can write it down that this is current multiplied, and look that this difference over here is this potential minus this potential. It's inconsistent with the arrow. If I mark arrow downward, it's conventional current over here. So I combine this minus with this difference and change the order of them and put voltage, which is this potential minus that potential. So the electric power delivered to an electrical element at any instant is equal to the product of the current flowing through this element and the voltage across this element. I have a before this, how about before the demonstration, why don't we go now to a resistor? How much power is delivered to resistor, because in the future we will see how to calculate power delivered to other elements. But so today I wanted to talk about electrical power dissipated in a resistor. In a capacitor, for example, we don't dissipate power. Instantaneously, power can be delivered to capacitor, but on average it cannot. Because we can get it back and forth. Or if we connect capacitor to a 9-volt battery, initially we will deliver power, but current very quickly will stop to flow. When the capacitor gets charged to potential difference of 9 volts, the battery is not capable to run any more current. So there will be there's no more power delivered to the capacitor. Let's now take a look at the resistor. Well, let's recall that in any element, power delivered in a particular instant is equal to the current at this instant multiplied by potential difference across the element at this instant. Now we can use Ohm's law, because if it is a resistor, current and voltage are related. So if I think, I recognize that potential difference across the resistor is equal to the current to the resistor multiplied by resistance. I can substitute it over here and get square of the current multiplied by resistance of the resistor. I can also think about it that current, also from Ohm's law, solve for current. It is potential difference divided by resistance. So if I substitute current over here, I will get square of the voltage divided by resistance. All right, now I wanted to show an experiment in which I am going to run current through a resistor. And for the resistor, I took steel wool. Because think what happens actually with that energy which is delivered. When electrons or charged particles flow through a resistor, these are electrons. When electrons travel through the resistor, they don't change their speed. They travel at a constant rate. through that resistor, assuming that we maintain potential difference. So, which means that kinetic energy of the electrons on one side is equal to their kinetic energy on the other side. So what happened with that excess of energy? Well, it is that it interacted with the lattice of the resistor and lattice of the material, the atoms of the material, and it transfers energy to those atoms. And in result, the resistor is being heated up. So it becomes warm. This is how a light bulb works. We take advantage of it. We run current through it, and electrons themselves don't gain kinetic energy because as they travel through the tungsten wire, they make the atoms of the wire to vibrate. All right, so here I have a 9 volt battery and this steel wool. And I'm able to warm it up. Can you see it? Did you see it? All right. It's already too rusted, so it doesn't burn anymore. All right. Now I'll give you a puzzle, summarizing what we discussed today. You probably, I mean, it's not, I mean, you still don't understand actually what does it mean that potential, that we have, that the output voltage is 110 volts, but in our outlets, but for a practical purposes, you can think that it's a constant voltage coming out which has 110 volts. Now Europe has 220 volts. This was a question which actually one of my colleagues asked me when I was in high school. Why don't we turn the lights on? He came with the question, what will happen if we use, can we connect somehow American light bulbs in Poland? And the idea was to connect them in series. So this is one light bulb, another light bulb. And they are connected to 220 volts. Now, American light bulbs are designed to operate at 110 volts. So, my puzzle now is, in this connection, will this light bulb burn first? This light bulb will burn first? Random or none? They are designed to operate at 110 volts, each of them. Let's vote. So who thinks that this light bulb will burn? 1, 2, 3, 4, 5, 6, 7. 7. Who votes for this one? 1, 2. We cannot say. Who thinks that it will work? 1, 2, 3. Robert, you are saying for both. Didn't you vote for this one?
You asked if it would work.
This time. Yeah, but when I asked if this one will burn, you raised your hand too.
Yeah, but I thought.
Okay. So Robert doesn't think that. So there were 3 that it will work. it will work. Over here you have, what do we have? I mean, it is a configuration which we discussed today. What? No, well, series resistors, correct, but I mean, it is a voltage divider, correct. It is a voltage divider, right? I mean, I forgot to say that. I assume that that you assumed it right away, that I take two identical light bulbs. Because if I had 40 watt light bulb and 100, then one of them would burn. But if I take two identical light bulbs, so if resistance of this light bulb is R, resistance of this light bulb is R as well. So potential at this point is going to be 220 volts multiplied by R divided by 2R, which means 110 volts. Potential here is 110 volts. Now, what is potential difference across this light bulb? 220 minus 110, which is 110. What's potential across this light bulb? 110 minus 0. It's still 110. So it is going to work. Well, so this will be all for today. Thank you for your attention and see you Monday.